In this short video, we're going to talk about a new concept called absolute convergence as it relates to series. So absolute convergence, we say that a series n equals 1 to infinity of a sub n converges absolutely, or we may say is absolutely convergent, provided that the series of the absolute value of the terms is convergent. So we're going to look at the series, the sum n equals 1 to infinity of the absolute value of n. If that series is convergent, we say that the original series is absolutely convergent. So let's look at an example. Let's show that the series, which terms are sine of n over n squared, is absolutely convergent. Now we know that sine can be positive or negative, and so I don't have all positive terms. But if I take the absolute value of the terms, now I have positive terms. And in fact, since sine of n is always less than 1, the absolute value of the term is less than 1 over n squared. So now that we're working with positive terms, we can use our comparison test. We know that the sum of 1 over n squared is convergent by the p-test. So our sum of the, I missed my sign here. The sum of the absolute value of sine n over n squared is convergent by the comparison test. And then a quick note here that sine of n over n squared, those terms can be positive or negative, but it's not an alternating series. You don't get one positive term, then one negative term, then one positive term, then one negative term. And even if that were the case, I think you get 3 positive terms, then 3 followed by 3 negative terms. But they don't satisfy the other conditions for the alternating series test. So we couldn't use the alternating series test, but we can show that the series is absolutely convergent. Well, does that mean that it's also convergent? And the answer is yes. And that should kind of make sense to us, that if the terms are getting small very fast, it really shouldn't matter in terms of the partial sums. If some of the partial sums are are not monotonic, that shouldn't impact it. And so if a series is absolutely convergent, then it's convergent. And let's see if we can come up with an explanation why that should be true. Well, let's just think about absolute values here for a minute. If I take a number and add its absolute value, it can never be negative. It could be 0. If the number is negative and you add it to its absolute value, then you would get 0, but it can never be negative. And then if I take a number and add its absolute value, it can never be more than twice the absolute value. If, in fact, it equals twice the absolute value if it's a positive number. And if it's a negative number, then it's equal to 0, which is certainly less than twice its absolute value. So what I can say then is now I can use the comparison test by looking at the series whose terms are a sub n plus the absolute value of a sub n. That's going to be a convergent series since I have an absolutely convergent series. So if I take twice that, that'll also be convergent as well. All right, so that's interesting, but how does that help us establish the fact that the original series is convergent? Well, now what I can do is look at the original series, and in each term, I'll add in the absolute value of the term and then subtract it out. That doesn't change the series, it just writes it in a different way because I'm just adding 0 to each term. But now I can view this as two series that I know are convergent. I just established that the series whose terms are a sub n plus the absolute value of n is convergent. I know that the original series is absolutely convergent, so the series whose terms are the absolute value of a sub n is also convergent. So I can break that up into two convergent series. So now I've got my original series written as the difference of two convergent series, so it must also be convergent. Well, if I have a series whose terms are both positive and negative, and it is convergent, but not absolutely convergent, we call that series conditionally convergent. And our example would be the alternating harmonic series. The alternating harmonic series is convergent, and in fact, we show that it converges to the natural log of 2, but the absolute value of the alternating harmonic series would give me, if I take the absolute value of the terms, I would get the original harmonic series, which I know is divergent. So the alternating harmonic series is conditionally convergent. In fact, any alternating p series where I have p between 0 and 1 is conditionally convergent. Same idea as with the alternating harmonic series. I know that if I look at the alternating p series, where p is between 0 and 1, these terms are going to be decreasing, and their limit is going to be 0 as long as p is bigger than 0. So that'll be convergent. But if I look at the series of where I take the absolute value of the terms, that just gives me the original p series. And the p-test tells me that p has to be greater than 1 in order to get convergence. So these are divergent. Well, something that's interesting and related to conditional convergence is something we call rearrangements. Now, we learned when we first started to learn how to add that if you have a finite number of terms and you find their sum, you can put them in any order you want, and you're going to get the same sum. There's no question about it. Now, if we have infinitely many terms, we have to be a lot more careful. If we have a series and we change the order in which we add the terms of the series, we get a new series which is called a rearrangement of the original series. Now, if you have a series that's absolutely convergent, then it behaves exactly the way a finite number of terms would behave. In other words, if you take any rearrangement of an absolutely convergent series, then the rearrangement is also absolutely convergent, and it converges to the same sum. Well, what if you have a conditionally convergent series? Well, we know that our conditionally convergent alternating harmonic series is convergent, and it converges to the natural log of 2. So let me call that equation 1. Let's multiply that equation on both sides by 1/2 every term. So then I would get this new series, 1/2 minus 1/4 plus 1/6 minus 1/8, and so on. And that sum will be half of natural log of 2. Let's call that equation 2. And now I'm going to add these two equations together in a particular way. So I'm going to just add the terms from equation 2 to the corresponding even numbered terms in equation 1. And when I do that, of course, if they have different signs, they'll add to 0. They have the same sign, and that only occurs when they're negative, both negative, then I'll get negative twice the value. But look at what I get. I get 1, then minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, plus a seventh, and so on. This is just a rearrangement of the original alternating harmonic series, but since I'm also adding natural log of 2 plus half a natural log of 2, I get a different sum. So when I look at a rearrangement of an conditionally convergent series, I might get a different sum. In fact, if you have a conditionally convergent series and you pick any real number, capital R, there exists a rearrangement of the original series whose sum is R. Now, it might not be easy to find that, but you can show that it exists. So conditionally convergent series have some very interesting properties.